Zachariah back here, and I'll be covering the geotechnical aspect of the project. The design of pile has become more critical because lateral loads have been considered more carefully, and increased emphasis has been placed on the analysis of the effects of vessel impacts, score, and earthquake events in bridge. The high strain rate, the temporary nature of the loading allow a substantially higher stress limitation than the statics design case. Based on the type of pile, the pile material ultimate strength must be greater than the ultimate pile soil resistance. Therefore, the factor of safety is applied to the material strength to obtain an allowable stress. Under combined axial and bending loading, the pile area A, the stiffness or moment of inertia I, and the distance from neutral axis to the edge of the section C must be defined to check maximum stress. The moment of inertia for various shapes may be computed with the following equations. It's also convenient to compute the elastic section model S. S is simply the moment of inertia divided by the distance to the outmost element. Cone penetration tests are conducted to obtain the cone resistance, the side friction, and the pore pressure. The soil type can be determined by analyzing these results. The value can also be used to design the shallow foundations through the estimation of stiffness and shear strength of cohesive soil. After cone tip resistance, stiff friction, and penetration pore pressure were calculated from the CPT data, the depth of each layer was determined. Layers are determined as shown: cone tip resistance versus depth, sleeve friction versus depth, penetration pore pressure versus depth, and friction ratio versus depth.
Hi, my name is Fadi Abdelmoudi, and as the hydraulics engineer, I'll be responsible for the following: lowering the tsunami elevation, slowing the water down, designing man-made channels, incorporating green energy and tidal turbines, and redirecting the water where it could be easily drained over time. And this is the beginning of the bay, and the yellow line represents the width of the bay, where the water enters, and where we calculated the discharge queue. Over here is the gate where we will be placing at the beginning of the bay, and this gate is going to lower the elevation of the water going into the bay. Now that the water is lower, it's going to be faster, and we're going to slow it down. We're going to slow it down by incorporating those man-made peninsulas, and those peninsulas are going to have rough surfaces, and they're going to be surrounded by large boulders, and we're going to use shrubs in the water, and which are also going to help slow the water down. By the time the water reaches the end of the bay, it's going to be low and slow enough to drain easily, and we place the jetty to separate the water flow between the river and the rest of the bay. Over here is the tidal turbines, and those are going to be used to harvest energy and create free electricity for the whole city.
My name is Iwo Mengistu Amara, and this is the structural hydraulic analysis of our project. This will include walls, trenches, pipes, channels, and lakes. The flow rate that we have calculated for this project is 36,000 cubic meters per second. And this is the way we calculated it. This is a view of the embankment area, which is going to be actually 1,050 meters long. The actual walls will stop the flow of the tsunami by mitigating the flow. The height of the walls will be 5 meters, and the trench will be 10 meters wide. We have done a seismic analysis with the Seed-Whitman approach. This is the view of the wall, the second wall in the project, which will actually have a series of pipes that will lead to the channel that will lead to the lake. The pipes are at a diameter of 1.5 meters and a height of 5 meters. This is actually one section of the wall, which is 30 meters wide. which is the smallest section, so you could view it. The flow rate of the pipes is considerably less than the flow rate of the channel and the flow rate calculated at the beginning, but since our first hydraulic engineer has mitigated the flow, this is plenty, this is enough. This is a cross-sectional view of the channel that we will be creating, which is a trapezoidal channel, which will have a height, a depth of 15 meters and a height of 16 meters and a width of 45 meters. That will lead to a lake. The flow rate of the channel will have 38,000 cubic meters per second if at full capacity. This is actually the Manning equation that we used for calculating the flow rate of the channel. This is a natural trapezoidal channel, and the design was for this presentation was borrowed from Andy Ward at the Ohio State University.
And the second portion of the structure design is the evacuation structure and the bridge. And the bridge will be placed just north of the bay, and it'll connect the main road leading into Kesennuma with the northern part of the harbor. Since if there's a flood event, access through the road it'll be impossible. And here's I used the Caltrans bridge manual to design the bridge, and it's just a typical cross section of a concrete reinforced concrete bridge with extended sidewalks for larger pedestrian traffic. And there'll be 3 clusters of 3 evacuation structures placed at separate parts around the harbor. And they'll serve, since those will be the first areas that flood, people can get somewhere safe as quickly as possible. And here's the CAD drawing of the second story flooring, and then supported by 15-foot high columns. And the white arrows indicate locations of evacuation structures, while the black arrows on top is the location of the bridge. And the style should fit into the pre-existing Kesennuma style, definitely stay touristy but not too industrial. And this picture is a perfect representation of what my design was.
My name is Pete Bredis, and I'm the construction engineer for the Kesennuma reconstruction project. The construction portion of this project will include a construction schedule, timeline, and cost estimate. The construction schedule will be broken down into 14 categories as shown. The main categories will be administrative, earthwork, water drainage and supply, structural construction, road system construction, and the final inspection. The Gantt chart shown here shows the breakdown of the entire construction process, which will start at the beginning of 2013 and finish by July of 2014. In order to estimate the cost of this project, the site was broken down apart as shown. All drainage and water distribution costs were determined using this image. As you may see, there is a water treatment plant in the lower right corner. This plant will treat all stormwater runoff and discharge it into the bay, which will promote cleaner fishing conditions. All unit cost data was obtained from the City of San Diego Development Services Department, and the construction and building costs were found on the Engineering News Record website. This data, along with the data gathered from the other engineers on my team, was used to find the final cost of the entire project, which came out to be around $150 million.